What if I told you there was a single hidden rule that connects every single flat shape you can possibly imagine? Well, today, we're going to find it. A powerful formula that links a simple little triangle to the most complex polygon. So think about it. A beehive, a stop sign, and a bridge truss. I mean, they seem totally random, right? But the answer that connects them all is this beautiful, hidden mathematical principle. And by the end of this, you'll see exactly how they're all governed by the same elegant geometry. All right, so to unlock the secret of all these bigger shapes, we've got to start with the simplest one, the true building block of geometry. We have to master the triangle. That's right, because once you really truly get the triangle, the rest of the puzzle just clicks into place. This is our foundation, so we need to make sure it's absolutely solid. Okay, so what's really cool here is that we've got two brilliant ways to prove the exact same fact. On the left, it's a hands-on approach. You can literally cut out a paper triangle, tear off the corners, and see for yourself how they fit together to make a perfect straight line. And then on the right, you've got a more formal proof that uses a parallel line to show that those three angles, well, they also combine to form a straight line. Both paths lead to the same exact conclusion. So, the crucial takeaway, the big reveal is this number, 180 degrees. You've got to remember this. It's the magic number for every single triangle that has ever existed or ever will exist. It doesn't matter if it's tall and skinny or short and wide, it's a universal constant. All right, now that we've got our foundation, that 180-degree rule, let's see how this thing builds. We're going to use this knowledge to crack the code of much, much bigger shapes. This is where it starts to get really fun. The key idea here is actually wonderfully simple. I mean, if we don't know the rule for a really complex shape, why not just break it down into shapes we do know? So let's start with a quadrilateral, any four-sided shape. Just pick one corner, a vertex, and draw a line to the opposite one. And boom, you've just split it into two perfect, non-overlapping triangles. And since each of those is 180 degrees, the total is just 2 times 180, which is 360 degrees. Pretty simple, right? Okay, let's try a pentagon. It's got 5 sides. From that same single vertex, we can draw 2 diagonals. And look at that. We get 3 separate triangles, so the total sum of its interior angles is just 3 times 180, which works out to 540 degrees. Are you starting to see the pattern here? Let's do just one more to be sure. A hexagon, 6 sides. From that one little vertex, we can draw diagonals that create exactly 4 triangles, and that gives us a total angle sum of 720 degrees. So let's see. 4 sides gave us 2 triangles. 5 sides, 3 triangles. 6 sides, 4 triangles. Yeah, the connection is becoming crystal clear now. So we've seen the pattern. Now it's time to turn that observation into a really powerful tool, something we can use on any polygon, no matter how many sides it has. And this just makes it so obvious. When you lay the data out on a table like this, the pattern is it's undeniable. Take a look at the column for the number of sides. We'll call it n, and then compare it to the number of triangles we made. The number of triangles is always 2 less than the number of sides. That's it. It's always just n minus 2. This simple little expression is the key that unlocks absolutely everything. And here it is, our master formula. To find the sum of the interior angles for any polygon out there, you just take the number of sides, n, you subtract 2, and then you multiply that result by 180. This is it. This is the hidden rule we were looking for. Okay, so now let's apply this awesome formula to a special, really beautiful class of shapes, regular polygons where everything is just perfectly symmetrical. So what is a regular polygon? Well, it's just a shape where all the side lengths are identical and all the interior angles are identical. Think of a perfect equilateral triangle or a perfect square. So if we want to find the measure of just one of those equal angles, it's a really simple 2-step process. First, we use our master formula to find the total sum of all the angles. Then, since all the angles are the same, we just divide that total by the number of angles, which is just n. Let's put it to the test with a regular hexagon, just like a cell in a honeycomb. Okay, so we already know the total sum is 720 degrees. And since a regular hexagon has 6 identical angles, we just divide 720 by 6. And that gives us our answer, 120 degrees for each and every interior angle. A perfect, elegant number. And what about that stop sign from our opening question? Well, that's a regular octagon. It has 8 sides. Using our formula, the total angle sum is, let's see, 8 minus 2, which is 6, times 180. That's 1080. Divide that by the 8 angles, and you get 135 degrees for each one. See? The math works every single time. Now, this might seem like just a neat math trick, but understanding these angles is actually incredibly important. It shows up all around us, in nature, in engineering, and in art. Think about that bridge truss we mentioned. In engineering, that unbreakable 180-degree rule of triangles makes them super rigid and strong. In design, knowing which shapes can tile together perfectly, like squares and hexagons, is everything. And in the world of technology, coders use these exact geometric rules to program robots to navigate and even draw the world around us. It's everywhere. Let's go back to the beehive for a second. The reason hexagons are nature's go-to shape for tiling is because their 120-degree angles are just a perfect fit. When you get 3 hexagons meeting at one point, you get 3 times 120, which is exactly 360 degrees, a full circle with no gaps. It is mathematically perfect. And this right here, this is really the core takeaway. This formula isn't some random rule that you just have to memorize for a test. It's a logical consequence of one simple, beautiful idea, that any complex shape can be understood by just seeing the simple triangles that are hidden inside of it. It really makes you wonder, doesn't it? We started with the absolute simplest shape, we looked for a pattern, and we uncovered a universal rule. So the next time you see a bridge, or a tiled floor, or a honeycomb, you'll know the hidden geometry that's holding it all together. What other patterns are out there just waiting for you to look a little closer?